Excellent. Right, over to you. Thank you very much.
So thank you very much for the opportunity to speak, and also thanks for attending this talk. Today we're going to talk about a work on head-on collision of vortex rings. And this is joint work with Kyudong Choi at UNIST. So this is the 3D Euler equations, incompressible and written in the vorticity form. Omega is the vorticity of the fluid, which determines the velocity at each moment of time. And the basic question that I'm interested in is whether for the solution of this vorticity equation, can we have infinite vortex stretching? So the term on the right-hand side of the vorticity equation is called the vortex stretching term because it can either increase or decrease the size of the vorticity. And whether the vorticity could become infinite or very large is certainly a mechanism for small-scale creation. And the heuristic picture is shown here. You have a vortex tube, by which we mean a region of almost uniform vorticity. And when the vorticity gets stretched, the tube needs to get thinner due to conservation of circulation and impulse. And when it becomes thin, it tends to get twisted in space, and it is well-known heuristics for energy cascade. So the question is whether it really happens and also whether we can actually prove. So this is basically the question of singularity for Euler. And there are classical works of Constantine and Gibbon, Moore, Stewart for blow-up of so-called infinite energy solutions. But in these works, the vorticity is already kind of infinite at the initial time. And then there are more recent blow works in which the vorticity could be actually compactly supported. And in these various works, the well-known Bill-Kato-Maeda criterion works, and in particular, at the time of finite time singularity, the vorticity, the maximum of vorticity, actually becomes infinite. And the problem with these results is that in the proof, lack of enough smoothness or presence of physical boundary plays an essential role. And of course, the blow-up of incompressible Euler in finite time for C infinity data is still open. And then a simpler question you can ask is, can you actually show infinite vortex stretching, at least in infinite time? So you can consider the simpler case of two-dimensional Euler first. And actually, 2 days ago, Professor Kiselev gave a great talk about this. And here's the two-dimensional vorticity equation, again written in the vorticity form. And you see that the vorticity is transported and bounded at infinity. The solutions are global in time. However, you can take the gradient, and then formally for the gradient of the vorticity, equation looks kind of similar to the 3D vorticity equation, and you have a stretching term on the right-hand side. And indeed, there's a long history, but I will not mention. there have been several infinite gradient growths for 2D Euler equations. And I'd like to mention very inspiring works by Denisov, Kiselev, Nazarov, and then, of course, Kiselev, Svera, Zlatosh, and so on. And this is usually done in bounded 2D domains. And then there's a cheap way of lifting the growth to 3-dimensional flows using the 2.5-dimensional construction. So this easily gives infinite growth of the vorticity given growth of gradient in 2D, but of course it requires the domain to be of the form D times the torus, and D is usually bounded domains for the infinite growth to occur. And then the question that I try to answer in this talk is that whether you can get infinite vortex stretching in the case of R3. So the simplest 3-dimensional flows are arguably the axisymmetric flows. And we, of course, had a talk about vortex rings yesterday. And the ansatz that we take is that the flow is axisymmetric and there's no swirl. It just means that the vorticity is a scalar in the direction of E theta. Here, R theta Z is the usual cylindrical coordinates. And then U is UR and UZ without the U theta term, which is called the swirl of the fluid. And then say that the vorticity equation simply becomes a scalar transport equation for omega theta. But you see that while the smooth solutions are global in time, this equation allows for vortex stretching. And this is precisely the mechanism of blow-up in recent work of Tarek Elgin. So for this equation, we would like to construct smooth solutions which shows infinite time vorticity growth. So the natural candidates for data are vortex rings, by which I mean just the vorticity is concentrated in some regions in space. So to briefly review what is the vortex ring, it just means a region of concentrated vorticity, and it has a tendency, when it's a single ring, it has a tendency to travel along the symmetry axis, which we take to be the z axis here. And there is even a very simple explicit solution called the Hill's vortex. The formula is just that omega theta is R times the characteristic function in cylindrical coordinates. And this is a picture of Hill's vortex ring in R3. And then I'd like to just mention that using some instability occurring near Hill's vortex, we could prove that the Hessian of the vorticity grows to some power in time for all times for smooth initial data. And but my question is whether the vorticity itself can grow in ad infinity. And of course, we can consider a case where many rings are interacting with each other. And then there are interesting interactions such as leapfrogging. But if all the rings have the same sign, then I do not see any mechanism for infinite vortex stretch. So if you know what it means, there's a Dyson model for vortex rings, and there's an associated Hamiltonian, which becomes coercive if all the rings are of the same sign. Namely, if they are rotating, all of them are rotating in the same direction. So the simplest setup you can imagine which could allow for infinite vortex stretching is when you shoot two symmetric rings with opposite sign. So the rings which are rotating with opposite directions. And this is what we call antiparallel vortex rings. So this is the perfect picture here. You have symmetry, and then, so here, this is the z-axis. A bit confusing, but now we are shooting two rings from side to side, and they are going to collide in a sense. Of course, they do not actually collide, if you know what I mean. So mathematically, we just mean that omega of theta, the vorticity, is odd function of z, and it has a sign on the upper half space. So in the upper half space, we say omega theta is non-positive, and then from the odd symmetry, in the other half, it is non-negative. And this is equivalent with having a single negative vortex ring on upper half space. And there have been extensive numerical works under this scenario of antiparallel vortex rings. And this picture is from this paper of Chu, Wang, Chang, Chang. And you see that these rings, which are initially apart, gets close and gets stretched to the R direction. So again, this is a bit confusing. The horizontal axis is the axis of symmetry, it's the Z direction, and this is the R direction in these pictures. In the meanwhile, I'd like to just mention that this kind of antiparallel flows were suggested as candidates for giving maximum entropy growth in the Navier-Stokes equation. And you can see these works of Ludoring, Ayala Protas, and so on. And I'd like to mention that already at this point, we will have some infinite vortex stretching result for the Euler equations. And it can be translated to unbounded entropy growth for the Navier-Stokes equations when the viscosity goes to zero. Okay, now so returning to the dynamics of antiparallel rings. The easy explanation is that there are three stages of motion in this flow. So initially, in the top left picture, when the rings are sufficiently far apart, of course, the interaction is very weak, and then each of vortex rings will travel as if it was only by itself. And then if they become sufficiently close to each other, they will need to get squeezed due to incompressibility. So they are expanding, kind of expanding the R direction, squeezing in the Z direction. And then once the rings become too thin, then of course instabilities grow to break up axisymmetry, and also swirl starts, and then the ring will break up into many pieces which have different topology and of course more stable. So that's the last stage of motion, which can be observed in both real fluids and numerical experiments with fluid equations. And you see that in these pictures, the Reynolds number is almost 2000, which is quite large. And you can see that if you even increase the Reynolds number further, the rings expand much further from the origin. So it can be argued that even in real fluids where there's always some viscosity, the first two stages are essentially inviscid phenomenon. And you can also observe that the maximum radius before dissipation kicks in increases with the Reynolds number, which suggests that infinite vortex stretching should be occurring for the Euler equations. Because you just record the Cauchy formula for axisymmetric flows without swirl. So if you just keep track of the vorticity along the axisymmetric flow map, the vorticity gets increased exactly by the factor of increase of the flow map in the R direction. So when the rings are expanding, it exactly gives stretching of the vortex by the same factor. So the natural question is, what is the rate of this vortex growth with time? And the difficulty in proving a rate exists is basically there is no known stability for this kind of flows. And instead, we rely on some monotonicity or maximum principles, if you want, that we now present. So this is a very simple statement. We assume that the flow is antiparallel, and then it happens that, and of course we assume that the solution, the initial data is smooth, so the solution is defined globally in time. And then it happens that these quantities are monotone in time. So this P is defined on the upper half space. So R and Z are both positive. And this is the integral of R squared against the vorticity. So record that the vorticity is negative on the upper half space. So minus vorticity is positive. So P is a positive quantity. And similarly, Z is also positive quantity. And it turns out that P are increasing and Z is decreasing with time. And now you record the conservation of the integral of omega. But note that this integral is not against R dr dz, which is the Lubeck measure in R3, but it's integral against dr dz. So it is not the L1 norm of vorticity, but it is the L1 norm of vorticity divided by R. Since this is conserved, you see that the decrease of this quantity Z is saying that the average of Z coordinate on the support of vorticity is decreasing with time. And similarly, increase of P simply means that the average of R squared on the support is increasing. And I'd like to just mention that the proof is actually not trivial, unlike the 2D case. So in 2D case, you can assume that the vorticity is odd symmetric with respect to both axes, and then similar quantities are monotone in time. There, the proof is basically trivial, but in this case, you first need to integrate the kernel in the angle. And unless you really use the representation of the integrated kernel in terms of special elliptic integrals, it is actually very difficult to see that the time derivative has a sign. Anyways, based on these monotonicity formulas, we can derive many infinite growth results. So first, rather simple consequence is that we can prove the existence of a C infinity data whose unique global solution goes through infinite growth of all the C alpha nodes. So this is just barely short of proving infinite growth of L infinity. You can actually show that any reasonable modulus of continuity for the vorticity becomes infinite. And the idea of the proof goes back to these words that I mentioned earlier, proving infinite gradient growth for two-dimensional Euler. Except that in our setup, the domain is R3, so there is a lack of stability, which we need to overcome. So let me explain the proof a little bit. And the paradigm is the stability of the instability. 2 days ago, Professor Kiselev gave a wonderful talk. And it is paradoxical. If you want to prove stronger instability, you need to have stronger stability. And then what are the sources of stability? I guess the most useful are conservation laws and monotonicity, symmetry, and so on. And this having many sources of stability is the basis of proving growth or vorticity and its gradients. So let me briefly record the structure of the arguments, first in the two-dimensional case. So the very basic idea is to cut out from the Bahuri-Sherman singular steady state. So to make the exposition simple, let's say the fluid is contained in a sphere, it's a 2D domain. And if the vorticity is identically 1 on this entire sphere, then this is a steady solution. But what you do is you cut out the steady solution near the boundary, and then you can, of course, make it smooth and vanish on the boundary. And the point is that this is stable because it is equal to +1 in almost all regions of the domain, but the vorticity is only being transported in 2D. So it is stable. It cannot change dramatically its shape due to area conservation. And then this induces a hyperbolic flow near the origin. So you take some non-trivial vorticity profile at the initial time at x equal to 0. So for example, you can take the vorticity near 0 to be x1 times x2 cubed. That's an example. And then this hyperbolic flow will send this x2 axis near the x1 axis. And this is the mechanism for gradient growth. And a technical and fundamental result is the Kiselev-Sfera-Key lemma, which gives some kind of expansion of the velocity in this setup. So at least near the origin, the lemma says that the velocity is hyperbolic, and this term I is some integral based on the vorticity. And having the whole point of cutting out from Bahuri-Sherman is that it fits a global in time lower bound of I, which sustains the strength of hyperbolic flow at the origin. And basically, this is the proof. And now in our setting, extending the key lemma to axisymmetric setup is kind of straightforward, and its versions have played a fundamental role in recent work of In-Jee. So it's basically the same dilemma, except that, of course, in UG, you have minus 2G instead of minus C. This is not a typo. And again, in our case, as we have seen in these simulations, the vortex ring is kind of escaping to infinity, and this will reduce I. And in principle, this mass of vortex ring could escape in many directions. It could escape to Z direction and R direction. However, escaping to Z direction is prohibited due to the monotonicity lemma that we have. Basically, only half of mass can escape in Z direction. And the mass actually escapes to the R direction, but it only helps because it gives vortex stretching, which is what we wanted to prove in any case. So based on contradiction argument, either it escapes to the R direction, in which we get vortex stretching, or it does not. In the case, we repeat a two-dimensional argument for gradient growth. So this is the proof of our first theorem. And now, again, as a more quantitative application of the monotonicity lemma, we can get universal growth rates for the quantity P, which is actually nothing but a vortex impulse. And we have a universal growth rate under, of course, antiparallel assumption. And we are assuming that the initial data is reasonably small so that the solution is global in time. And we get some vector, P of T grows at least to T to the power 2/15 minus epsilon. And as the corollary, this gives infinite growth of the support diameter for vortex rings as time goes to infinity. And this is some picture that I quickly drew. So this ring is going out to the R direction. And in an average sense, location of vorticity at time t is at least t to power 1/15, because R squared is t to 2/15. And let me just explain how it can be proved. And the Prof ideas have been strongly inspired by Iftimi, Sideris, and Gambini, who proved a similar result in two-dimensional flows under the odd-odd symmetry. And the key idea there is to obtain a lower bound on P dot only based on conserved and monotone quantities. And it turns out that in our case, it is not really possible because the scaling is now different and the equation is not isotropic in R and Z. So what we could instead prove is that the kinetic energy, which is E, is bounded by a combination of P and P dot. So P is very large, so it is useful to have some vector of P on the right-hand side, except that it decreases the growth rate we get on P dot. And this quantity X, if you look at this expression, it only involves conserved quantity and monotone quantities. So G is, of course, monotone decreasing, and P is monotone increasing, but you see that the power of P in X is 1 minus Q over Q, which is negative. So this quantity X is only decreasing in time. So we can bound X with X at the initial time. Then we can integrate this key inequality in time to get a lower bound on P in time. And the rate T to the 2/15 comes from the technical restriction on Q, in which we can prove this kind of inequality. And the proof is not very complicated. Here the kinetic energy can be written as a double integral involving the vorticity and some kernel. And you bound the kernel based on whether R is less than or Z or vice versa. And then you get these two terms in X. So the vortex impulse grows with time. And now the growth of the vortex impulse can be used to prove infinite growth of vorticity LP norms, except for a technical condition, which is written here. So assume that for some P, the initial vorticity has compact support and satisfies this inequality. And it is not difficult to see where this inequality comes from. So what we have is the growth of P, and P is integral of the vorticity against R squared. And we want to translate that growth to a growth of vorticity in LP. So for the interpolation to work, we basically need that the area in which the initial vorticity is too small is not too large. So basically what happens is that if the vorticity is basically very close to zero everywhere, having large impulse does not really contribute to large LP growth. And the quantity that we need to interpolate with is exactly this quantity that is written here. And this quantity is conserved in time. And that is very important because this quantity involves R over omega, which is conserved along trajectories. This is so-called cushy, which is conserved along particle trajectories in axisymmetric flows without swirl. And the rate of LP growth, of course, depends on this assumption. But ideally, when delta is sufficiently close to zero, we get that the LP norms are growing with the rate T to the 1/15th. And an unfortunate fact is that this key assumption 1 is not satisfied for C infinity data, but it is satisfied for several classes of vorticities. First, it is satisfied for vortex patches, because vortex patches can be strictly bounded away from zero on its support. And of course, the boundary can be C infinity, there's no problem with that, and it propagates globally in time. But this assumption 1 can also hold for vorticity with C1 alpha regularity with some alpha. So in this case, the vorticity is not C infinity, but it is C1 alpha. And of course, then the velocity is C2 alpha. And this gives pointwise growth in time of the vorticity at infinity. So infinite vortex stretching actually occurs. And then there's some additional argument we can perform, which ensures slightly larger growth. And let me just finish with some discussion of this kind of direction. So basically, the question we can ask is, what is actually the maximal possible rate of vortex stretching in these axisymmetric flows without swirl? When two rings are collide, what is the rate? And then, of course, you can go back and see the original global well-Posner's proof. And my bounds say only that the vorticity could grow exponentially in time. That is a simple estimate you can do. But in a very interesting work of Childress, he suggested that the upper bound on vortex stretching should be 2t squared. And actually, he has another argument, which is better, in which he claims that the maximal rate should be t to 4/3. And this is very interesting because Feng and Sfera could rigorously prove that t squared is an upper bound. And more recently, Childress and Gilbert did numerical simulations in which they not only claim that t to the 4/3 is the upper bound, but it is also achieved in this geometry by so-called Sadowski vortex, although you need to take into account vortex stretching in axisymmetric flows. So this could be the correct answer. And again, our lower bound is basically t to some small number, 1/15 or 0.13. But in the two-dimensional case, the result is sharp. A simple estimate gives that if the vorticity is odd with respect to both axes in R2, the support diameter of the vorticity grows linearly in time because there's a uniform upper bound on the velocity, which you can easily prove. But then, if Timmy, Sideres, and Gamblin also prove that this linear growth is achieved, this is completely sharp. So the last comment that I want to make is that, of course, it is tempting to apply the Dyson model for vortex rings. So So this is the axisymmetric analog of famous point vortex dynamics in two-dimensional flows. And you can try to compute with Dyson model what happens if two vortex rings are colliding, assuming that, of course, these vortex rings have a very small cross-section. That is the basic assumption in the Dyson model. But unfortunately, Dyson model says that the dynamics is exactly the same as in the two-dimensional case. But this is completely false, because then it would force the vortex stretching, which is linear in time, which then means that the cross-section goes to 0 with rate 1/t, but then the very basic assumption of localized induction approximation breaks down. And it is much more reasonable that the vortex rings gets closer and closer to each other. And the correct answer is faster than t, as Childress claims. So I think that's it. Thanks for listening.
We cannot hear what's happening in the audience. Can you please use the microphone?
Yeah, thanks. I cannot hear anything.
Can hear. Can hear now?
Yes.
Can you hear now?
Yeah.
Okay. My name's Robert Kerr. I'm from the University of Warwick. And there's some things in your introduction about the colliding vortex rings that you should know about. So there's this very nice paper in Physical Review Fluids from 2018 by a group based at Harvard. One of the authors is Brenner, but the lead author is McEwen. And it's a combination of experiments of the colliding vortex rings and nice calculations. And I think it's appropriate that you look that up and you understand what they're saying and include that. There's another paper that's slightly different in, I think it's 2020. It's one of many papers by Yao and Hussein in JFM. And it has a title on the singularity of Navier-Stokes. And sort of like you, their conclusion is there aren't, but it's colliding vortex rings, but at a tilted angle. And then the other thing is my own work, which is an association with John Gibbon that was started at the Newton program here 10 years ago, where I asked John if he could come up with a version of his vorticity moment expansions for Euler that I could apply to Euler numerical data. And he did that. It's in the proceedings of that Newton meeting from 10 years ago. And I applied it. I have a JFM paper in 2013 applying it to antiparallel vortices with a perturbation. And the conclusion was that for Euler, the maximum growth was at most doubly exponential, which would not be inconsistent with what you're telling us now. And if you want a really nice explanation that ties those two together, John Gibbon gave a presentation at the 80th birthday party for Uriel Frisch last December. And so you can pick that up online. It's done through Tata Institute, I think, in India, although we were all over the world when we saw it and made the presentations. And I think it'd be really useful if you look that up and see what John Gibbon had to say. That's what I wanted to say.
Thanks, Bob. Any more questions? Any questions online?
I have a question if there's nobody has questions.
Go, Idris.
Yeah, thank you. Thank you for beautiful talk and for your patience of really presenting things slowly and letting us really get into this. There is one slide you have shown that you can prove that for every alpha, if the initial data is completely supported, the supremum in time is equal infinity.
Can you see the slide now? I'm not.
Yeah, this one, you passed it, go back. Oh, yeah, here, this one. The lean
This
in,
one or?
yeah, this one, the lean in.
Yes.
Yeah. So this result, can you elaborate more about this result in some sense? I mean, is this for what kind of conditions?
Yes, yes. Yeah. Thank you very much for the nice comments. And this is so late near the end of my talk, I showed that if the initial vorticity is of the patch type, which is supported away from zero on the support, then for Euler, we could prove infinite growth of all LP norms starting from t equal to 2. So that's what we have with a quantitative rate. But then what we can then do is use the same patch type axisymmetric no-swirl initial data and solve Navier-Stokes with viscosity nu with the same initial data, but changing the viscosity. So for each viscosity, we know that the solution is smooth global in time, decays at time infinity. But for each nu, there will be some time when omega nu in L2 attains its own maximum. And then as you take nu to 0, this maximum should become infinite. The proof is really simple, and you just assume towards a contradiction that this is not infinite, but then you perform some simple implicit limit argument, and then you obtain that the limiting Euler solution should not grow in L2 in space.
Yeah. So this is for the same initial data. All these you change only the viscosity, but the initial data is the same, correct?
Yes.
Okay. Actually, my question was not about this slide, but this was important, and it's about the one with the C alpha.
Yeah.
Yeah, this one. Okay. So there exists a compactly supported datum with unique solution. This is a 3D, correct?
Yeah, this is just axisymmetric without swirl. Yes.
Okay, and now when you talk about compact supported away from the, you talk about away from the axis as well. You mean like the support does not contain the axis, correct?
Oh, so actually we did it in a way that support contains the axis, but the solution is still C infinity in R3. So as long as it vanishes linearly in R as R goes to 0.
Exactly, that's it. So
Yeah.
Because you need this somehow omega over r to be in L infinity in order to get global existence.
Yes.
Okay. Thank you very much. Yes, perfect. No, I thought that's what you meant, and thank you for the clarification, and thank you for beautiful talk. Really, I really enjoyed it. Thank you very, very much.
Oh no, thank you very much for attending. It's great pleasure to have you.
Are there any more questions? Yeah.
And John, very nice talk. So I was wondering if you put this in a cylinder. I'm thinking of the connection with the how Luo work. So should I think that just what happens in 2D happens, or what are your thoughts if you put this in a cylinder? I mean, I should think that the growth is doubly exponential, like in 2D, because what happens near the boundary is like in Kizilov-Schwarzschild, or?
Yes, and you are absolutely right, and that is indeed proved in this paper of Tom Do, which I mentioned in this list. So, as in Kizilov-Schwarzschild, if it's cylinder, and of course the data should touch the boundary, otherwise it's a difficult problem. But Tom Do exactly have done.
Okay. Thank you.
Yeah, thanks for the question.
Any more? Well, let's thank In-Jee again for a very nice talk.
Thank you very much.